Welcome to the lesson, Air Data System. The Avro Air Data System is centered around two digital air data computers. Both ADCs receive input from the aircraft's pitot-static sensors, angle of attack vanes, and total air temperature probes to provide various digital parameters. A transfer switch is fitted, enabling all ADC information to be obtained by a single ADC should one fail. An Air Data Accessory Unit converts information from both ADCs into an analog form and supplies aircraft systems which do not operate on digital data. The Avro RJ has three pitot-static systems, designated 1, 2, and 3. Systems 1 and 2 are the primary systems and supply pitot and static signals to ADCs 1 and 2 respectively, which together with the Air Data Accessory Unit form the Air Data System. The number 3 system provides pitot-static for the standby airspeed indicator, altimeter, and the pressurization triple gauge on those aircraft fitted with an analog pressurization system. Each static system, S1, S2, and S3, have two vents, one on each side of the aircraft, which are connected together in order to reduce side slip errors. The number 1 pitot head, P1, is located on the left side of the nose. The numbers 2 and 3 pitot heads, P2 and P3, are located on the right side of the nose. Two total air temperature probes are used. Number 1 on the left side of the nose, which provides temperatures to ADC 1, and number 2 on the right side of the nose, which supplies ADC 2. The QPOT pitot-static head is located below the TAT probe 1. The integrity of the QPOT pitot-static supplies is monitored by two differential switches, which use P3 and a dedicated static source, S7, as their reference. If a difference is detected between the QPOT pitot-static pressures and the monitoring pressures, rudder elevator Q fail illuminates on the central warning panel. Static sensors S4 and S5, each with a vent on each side, are used by the discharge valves as a reference for maximum cabin differential pressure protection. The front discharge valve uses S4 and the rear discharge valve uses S5. When ditch is selected on the pressurization controller panel, both discharge valves fully close. Therefore, in order for the discharge valves to provide negative relief when ditch is selected, separate static sources are required for reference. For aircraft fitted with an analog pressurization system, this is provided by S3 for the front discharge valve and S8 for the discharge valve. The S8 source is deleted and the discharge valves interconnected via a static line when digital pressurization is fitted to the aircraft. ADC1 is powered 115 volts essential AC, and ADC2 is powered by 115 volts AC2. Each ADC accepts data from the sensors and provides various outputs to aircraft systems and for display on the flight deck. Altitude. Each ADC has barometric altitude, which is automatically corrected for position error using information from the angle of attack vanes. This correction is known as Static Source Error Correction, SSEC. Altitude is displayed on both servo altitude when a barometric correction is made. Pressure altitude is also continuously available for other systems, such as the Mode S transponder, to provide altitude reporting. Airspeed. Each ADC provides computed airspeed, calibrated for position error, which is displayed on the EFIS from 30 knots upwards. True airspeed is supplied to the GNSX or GNLU 910 for navigation calculations. Above VMO or MMO, the ADCs provide an overspeed warning and intermittent horn to accompany the EFIS visual indications. Vertical speed. The ADCs blend barometric rate of change derived from static measurements with vertical speed data derived from the IRS to provide an indication of vertical speed on the EFIS. Should the IRS data become invalid, the ADCs are able to provide a degraded vertical speed indication. When this occurs, the vertical speed numerical readout turns from green to white. Both of the ADCs are the Air Data Accessory Unit, which supplies several discrete and full-range signals to the following systems. During the external checks, it is vitally important to ensure that all pitot and static vents are unobstructed and their covers and plugs have been removed. Now, click yourself through the external checks. Check the pitot head P1. Check AOA vane is undamaged. Check the TAT probe 1. Check the Q pot. Check the right static vents S1, S2, and S3. Check the pitot probe P2. Check AOA vane is undamaged. Check the pitot probe P3. Check the TAT probe 2. the static vent S7. Check the left and right static vents S4 and S5. Check static vent S, analog pressurization only. Test. Each ADC can be tested from the ground test panel using its associated test button, ADC Test 1 or ADC Test 2. Pressing and holding the relevant test button will cause the altitude to increase on the corresponding altimeter until after approximately 4 seconds the off flag is displayed, as well as the red speed Mach and vertical speed annunciations on the corresponding PDF. The intermittent overspeed horn will sound for at least 2 seconds, indicating the system has passed. Should an air data computer fail, the following indications are displayed. You would now refer to the Quick Reference Handbook, QRH. The QRH A&E check pronunciation provide us with useful information on how the failure affects other systems. Let's go through the procedure. 1 ADC lost. The procedure first tells us to disengage the autopilot and turn off the autothrottle and the flight director. Then the air data transfer switches to both to the serviceable ADC, in this case ADC 2. Selecting the air data transfer switch to the serviceable ADC will restore the indications to all the instruments and permit the air data accessory unit to be fully operational with a single ADC. A yellow ADC 1 or ADC 2 appears on the bottom of both PFDs to indicate which ADC is feeding both sides. Now we select the transponder altitude selector to the serviceable ADC. Monitor standby instruments as sole redundancy and as no air data comparator caution will be given. Then re-engage the autopilot, flight director, and autothrottle as required. This completes the A&E checklist, loss of ADC. There is no fail indication for a fault within any of the ADC's pressure inputs. Such a condition would generate a speed miscompare warning. Again, let's look at the QRH. A&E checklist comparator first tells us to compare the airspeed of the left and right PFD with a standby airspeed indicator. The PFD, which shows an airspeed coinciding with standby ASI, should be used as the correct signal. Now, we disengage the autopilot and turn off the autothrottle and flight director. The serviceable ADC is then selected using the air data transfer switch, in this case, ADC number 2. The transponder altitude selector is now selected to the serviceable side. Monitor the standby altimeter and airspeed indicator as it is the only redundancy. The autopilot, flight director, and autothrottle can now be re-engaged as